Today we will be discussing the electromagnetic radiation spectrum. Electromagnetic radiation is a form of energy that exhibits a wave-like behavior as it travels through space. The first thing that we're going to look at is the parts of a wave. So here I have drawn out a wave and I have labeled certain parts of it. From this center line to the top of the wave is labeled as A, which stands for amplitude. The amplitude is going to be the height of the wave from the origin. Amplitude is measured in length units, such as meters or centimeters. Next, you can see from the top of one wave to the top of another, I have labeled that as B. B is going to be my wavelength, whose symbol is going to be lambda. And it is the distance from one point on a wave to the next point that is exactly like it. My wavelength will be measured in length units such as meters, centimeters, or nanometers. The next portion of the wave that I have labeled is at the very bottom of this wave. That is labeled as C, and that is my trough. My trough is going to be my lowest part of my wave. Next is D. D is labeled as the very top of my wave, and that is known as the crest, and it is the highest point of my wave. Lastly, I have the label point E on the line, and that is going to be my origin. It is the line separating the two sides of the wave. Now we're going to talk about aspects of a wave that can't be seen necessarily from the picture of a wave, but attributes of that wave. So the first is going to be frequency. This can either be symbolized by a lowercase f or nu, this letter nu. Frequency refers to the number of wavelengths that pass through a given point in 1 second. The unit given to frequency is hertz or per second. Continuing on with electromagnetic radiation in general, electromagnetic radiation spectrum is how we illustrate all of the forms that electromagnetic radiation can take. This is my illustration of the electromagnetic radiation spectrum. I highly recommend that you pause the video to copy this down, but I do want to just point out a couple of things. The numbers that I have added to my electromagnetic radiation spectrum are in reference to the wavelengths. That's why they are in length units. I also want you to notice that we span quite a large amount of wavelengths, and I have a very, very narrow piece of visible light that is represented by this rainbow. We can only see wavelengths between 400 and 700 nanometers. This is a very, very small piece of the overarching electromagnetic radiation spectrum. Again, I recommend that you pause to take down the electromagnetic radiation spectrum. Some notes about the electromagnetic radiation spectrum. Wavelength is going to be inversely proportional to frequency. Remember that my wavelength is how far in between two of the same portions of the wave are, and frequency is how often I can form a complete wave in a second. If my wavelength is very long, it will take me a longer time to complete the wavelength. So the frequency, how often I can complete a wavelength, will be decreased. So they are inversely proportional. If wavelength is large, then frequency is small. If wavelength is small, then frequency is large. The speed of all electromagnetic waves is 3 times 10 to the 8th meters per second. The speed of light is also 3 times 10 to the 8th meters per second. The variable or constant that we are going to be utilizing for light is lowercase c. It's important that it's lowercase because we're in chemistry, and an uppercase c is carbon. So c is lowercase for light. This relationship between the wavelength, frequency, and the speed of light you will need to memorize. And it is this. C, the speed of light, is equal to lambda nu. Lambda is our wavelength and nu is our frequency. So the speed of light is equal to the wavelength multiplied by the frequency.